Fluor Canada, we have the opportunity to design, conduct 3 different kinds of the renewable diesel project, including 2 diesel greenfield diesel new project and 1 revamp project for coal processing as well. One of them actually is under construction right now, and there's one I'm still doing coal process study at this moment. It's a good opportunity for me to share what we have done with this experience. Just a little bit fly here for the advertise. So Fluor is one of the biggest engineering company in the world, and we have designed, built all the different industry facilities or the projects, plants over the 6 continents. We provide comprehensive solutions for clients in energy and chemical, government, life science, and advanced manufacture, power, mining metals, and maintenance actually as well. We serve more than 4,000 clients over 60 countries there. We always ranked around 250 between 300 in the Fortune 500, always be there. We have more than 40,000 employees around the world. Currently, Fluor has survived 110 years already. Okay, next one. It doesn't do this. Okay. Sorry, yeah. And just go up briefly, probably just first I will just touch what is a renewable diesel and what is a production process has been available so far. And the next I will talking about briefly about the feedstocks, what kind of feedstock you can use to make renewable diesel. And after that, I will briefly do a high-level comparison between what is a conventional diesel and what the renewable diesel in terms of the processing technology there. Last, not the least, I will talk about the challenges we have experienced in design this kind of units there. So before this talk, let's just do a I just want to clarify some of the definitions between the renewable diesel and biodiesel. I found many people has a confusion here in these terminologies. Here, at least for this talk, we refer to the biodiesel is basically produced from the trans-esterification process, which is purely like a monoalkyl ester, which is measured by the fatty acid methyl ester. It's just called the flame analyze only, coming from there. And renewable diesel, we specifically refer to those diesel fuels produced from the hydrotreating process here. So basically, typically we're using vegetable oil. In Canada, we're using canola oil as a feedstock, or we're using part of them using animal fat as a feedstock only. So this renewable diesel basically specifically refer to that part. So biofuel is defined of the sustainable source of energy composed of the long chain of the fatty acid, which is derived from the bioresource, such as vegetable oil or animal fat. It is basically these kind of the materials, which is composed very similar composition. It is composed of like 3 different fatty acid chains, which is linked with one glycerol, small component glycerol there. So the renewable diesel process is try to just broken those chains of those 3 long chains there. So making those products from those 3 long chains. Those 3 long chains basically is a normal paraffin only. Yeah. So despite of the bright prospect of the renewable diesel, its commercialization actually quite limited worldwide. The major obstacle is because the high cost of the resource of the feedstock. Yeah, for canola oil, we are used in this processing is the feedstock itself taking part about 70% of the total cost. So it's you can imagine it's a huge portion of your production cost there. So to reduce the cost, one of the natural ways you try to using some low cost. Thank you. Yeah, we have try to use some low cost materials such as animal fat, cheap feedstock stuff to feed your plants, so that you can manage to reduce the cost of the production. Okay. Specification between diesel fuels and the biofuels. So it's just simple comparison based on the standard measurement of ASTM there. Okay, so renewable diesel, you can see here, is basically it's a 100% blendable. It follows the conventional diesel fuel standards here. On the other side, biodiesel here, it's basically it's a separate standards. Just want to emphasize here, oxygen content is quite high from the pure biodiesel production. Let's see here is 11, typically more than 10% there. Another, you need to notice those biodiesel productions from the esterification here, the heating value is also relatively low compared to the conventional method of renewable diesel method. But because of those two factors there, typically there's a limitation. You try to blending these stuffs into the conventional diesel pool, you have a limitation there. So typically, I think US limited to you about 7 to 7, maximum 8% of blending about only, cannot blend more than that. It's another high-level comparison just for the compare the quality of the products there. This chart coming from the UOP Honeywell UOP process, but it's the similar licensor can produce the similar products quality with the same quality here. One thing I want to mention, just as emphasize here, it's a green diesel. Basically, we're talking about the renewable diesel here. You see the city number is quite high, which is high valuable. Another thing is you see city number is high, heating value is high, and excellent coat property. That means you less viscous stuff, right? Yeah. So it's because of those, it's actually quality is better than the conventional diesel. It's really popular. It's highly required by the market. Here, just briefly touch what are those available renewable diesel operating plant facility currently. Currently, you see above the dozens of the facility operating around the world. And the two things you want to take off from here is number one is you can see the diversity of the feedstock driving the process development here. Here there's different licenses here, like Nestor, Diamond Greens, all they are using but different feedstock. Nestor, this process here, they claim using non-edible oil. And Diamond, this project using animal fat only. And this one actually using tall oil coming from the purple plant, that one. Okay. Another takeoff I want to note today is you may want to reevaluate your view of the plant scale here. You see 20,000 barrels per day here unit is relatively big already compared to what we typically see in conventional one. Conventional 20,000 barrels is not big, but popular. But here in terms of renewable diesel, that scale is quite big already. It's very costly. We just built one tanker. Low cost 20,000 barrels per day, typically about $4 billion over. You have to take there. It's very high intensity of the hydrogen consumption, energy consumption as well. It's high cost of unit as well. So usually it's running from like 2,000 to 20,000 scale. That's currently what we have here, available in the market here worldwide. A little bit of the chemistry high level here is, as I just mentioned, that all the feedstock we are using, like vegetable oil, mainly composed of we call it triglycerides. Basically, it's the 3 long chain of the normal paraffin, which is linked by the glycerol. So what we try to do, we try to break those bonds, oxygen bonds, by hydrotreating process. Usually it's under catalyst, you put at a high pressure heat, like a conventional hydrotreating process, and then that bonds will get broken. So what left over is the normal paraffin products with carbon number from 16 to 18 around. Most 17, 18 is a higher concentration, a little bit 15, 17 there. The byproducts is propane, water, and CO2 here. Those are byproducts there. So maybe it's a little bit, let's take a close look at the reaction paths there on top of those chemistry here. There are many different reaction paths, but the main reactions happening is about 5 or 4 different paths. The number one is the deoxygenation path, which is a designed one. So which is a really highly designed. You want to make products for the C18 products here and the water here. This is one is a high hydrogen consumption here, high product yield, which is really you want preferred reaction path. The second one here is decarbonylation here, so which is consuming less hydrogen and making products of the C17. And what is you don't want is the CO actually here, got a CO there. Unfortunately, you cannot avoid. It's just coming with a reaction path there. This one is a decarboxylation reaction as well, which is basically the making C17 normal paraffin with the CO2. That's also byproducts as well. It is less preferred, but still you cannot avoid. It's happening there. There's a one more here. I think what's part here. There's 2 side reaction also going is a reverse water shift as well, which is converting CO2 to CO. There's another methanation reaction happening as well, which is making methane from CO here. This one also unwanted, but it's happening same time in the reactor there. Something you cannot avoid, but you try to minimize, mitigate it. So just a very high level comparison of the conventional diesel fuel production process and the renewable production process. It's very similarities there in terms of plant configuration technology, but when you look at details in the details of the technology, there's a quite significant differential there. So number one is the feedstock. You see that renewable diesel, we're using some units using totally new feedstock like vegetable, animal fat. Some facility just blending a portion of them. So we designed both different project with there, blending those one. But as soon as you blending the vegetable oil and animal fat into the feedstock, immediately you're facing all these challenges here. So in terms of feedstock here, when you're blending those very nasty stuff into feedstock, you have to pre-treat them, right? To remove all the impurities and to handling the sour, the acid gas, fatty free acid gas in the feedstock, which is coming with the vegetable oil, those one there. So that's you handling those sour feedstock, you have to handle the corrosions, right? That's and the viscous coat property as well, very viscous fluid there. But in terms of the hydrotreating process here, conventionally, it's basically it's dehydrosulfurization, dehydronitrogenation, right? But in here, in renewable diesel, you remove the oxygen. We call it the deoxygenation process. And you remove you change the coat property by isomerization. So we call dewaxing process there. There's different process here. So reaction catalyst work is significantly different. You specifically design the specific purpose of the catalyst to do that one. So you see, in conventional, you're using nickel, moly, and cobalt based. But in renewable diesel, you have to focus on the two different types of reactions or functions there to make it happen there. And in terms of the hydrogen consumption, conventional, you see renewable diesel almost double the hydrogen consumption compared to the conventional. That means you probably get a double the heat release as well. And you are making more propane because propane is a byproduct. So that goes to the LPG range of the years. You have a high off-gas production there. And another side effect of the renewable diesel, when you do have a higher hydrogen consumption, hotter temperature is that your reactor can easily get cooked because of the depletion of the hydrogen and the high temperature there. So you get very high chances to be cooked in the reactor. That means your catalyst bed easily get plugged compared to the conventional method. You will have a shorter running line. So currently, all the licensors, they can guarantee the running lines for the new renewable diesel unit is 2 years. And conventional units right now, we are running 4 years, 48 months, but for these ones, only 24 months from licensor guaranteed. It's half of the running lifespan. Of course, you have to handle CO2 removal because you're producing CO2, right? You have to put like any unit to sweeten the gas, remove the CO2 there. And you also need to find a home for the CO2 while you have to dump it right somewhere. You cannot just dump it to the atmosphere. You have to put it pipeline, sequestration, and sequence, right? Something other way, find a home there. Of course, the last is you produce some water and you have a corrosion issues. You have to handle this specifically, put more attention there. So let's just go back to the sea. I mentioned that the feedstock is basically quite challenging handling the renewable diesel process. So there's a very wide variety supply of the different feedstocks. It can be vegetable oil, soybean oil, palm oil, canola oil, all those can be used. The only disadvantage those was the food resource. So you're competing with the food resource. It's not a good thing, right? So animal fat is another alternative option of the feedstock. But it's very, very nasty, viscous stuff. You have to removing dealing with all those impurities and nasty stuff. Almost all the low quality feedstock has this problem. Has a lot of impurities which you don't want. You have to remove. For example, the animal fat we are used in one of the projects. You have to remove all the alkalized metals, which is all these element here being presented. You have to remove those. You have to remove the phosphorate otherwise you're making soap instead of the diesel. And there is always something like a polyethylene, some impurities there in those kind of feedstock. So you have to delete those one, remove it as well. It's quite a challenge for this, very costly and quite a challenge there. A typical pretreatment process, which is including these 3 different type of the process, which is the first one, the filtration. That's basically it's removing all those solids, impurities, those stuff you don't want it, and you have to go through the degumming process, right? Removing all the phosphorus stuff there, and the third one is a raising or bleaching process there. That one will ensure you're removing all the alkali metals you don't want it there. These ones like usually bleaching used to use using clay, kind of like a very high cost process there. Currently, there's a new technology we're using hot temperature acid treatment, high temperature, high pressure treatment there. That is quite successful, right? There's a new technology available. We can reduce the costs there. Because I just mentioned that this one has a high content of the free fatty acid, which is an acidic environment, which is very challenging for the materials. So you dealing with this stuff, you have to update all your materials to prevent the corrosions, right? Typically you have to use basically all the materials here need to be at least regular stainless steel. That means the equipment cost will be high. So another thing what we did is quite unusual, unique is we did a molecular modeling of the feedstock and for the process, right? There are quite a challenge for doing this kind of modeling, this kind of process for two reasons. Number one, the measurement test is not actually molecular level is not available yet. So people cannot identify individual molecules in those feedstock, but what they do that like a film analyze, give you the roughly lumped molecules only. So that's one challenge there. You know roughly what is there, but you don't know exactly what is there, right, in the feed there. Second challenge is currently there's no thermal package available in the commercial software like HYSYS, Aspen Plus, right? So you have to kind of like building your own in-house thermal package or modify it to make it reliable, use there. So we basically, for doing those design project, we build our own molecular level model. We build the molecular level using Aspen Plus and using NRTL thermal package there. So we based on this lumped measurements from the film analyzed there. We're using these lumped molecular information to build a model to represent the whole feedstock like a canola oil. What is you see here is there's a big difference between canola oil and animal fatties. What is different here is for canola oil, vegetable oil has a very high unsaturated content. That means a lot of double bond there. But on the other side, for animal fat, it's a saturated fatty acid content is pretty high, more than 40%. That's a very high content of the saturated stuff. That means for saturated stuff, we know it's basically like paraffinic materials, which is viscous, which is wax, right? It's challenging for dealing with those. We're using NRTL models mentioned, but similar package you have to kind of like develop it by your own. Well, what we did, we found, we're using 36 different triglycerides molecules to represent the whole mixture of the canola oil. Among those 36 triglycerides, there's 6 of them which is available, so you can find all the properties. Like a physical property, density, heat capacity, viscosity, thermal conductivity. So you can find those properties from we call it data bank, which is one of the ANCHE databases there. So you can find those 6 ones. So, fortunately, those 6 ones were actually quite popular. It has a high concentration of those canola oil. So we're using those 6 properties from 6 to estimate the rest of the triglycerides compounds. So by doing that, we are successfully to predict the property of the canola oil and the process fluid there. So we compared the predicted properties with the literature data, validated, they are in good agreement, which is good enough for you to make a process design there. So here, just showing an example of the comparison between the viscosity we predict for the canola oil as compared to the reported literature data there. So you can see that there's a good agreement between those estimated and the reported data there. So that's basically the kind of like a validate your thermal package there. So this is a typical available hydrotreating process available in the market currently. Now it's a simple sketch showing here. Basically, it's a two-step of the reactions, as just mentioned. So now the first one we call the deoxygenation. It's happening here. There's a reactor deoxygen. We call it H2O reactor, hydrodeoxygen reaction here. Second one is the DWAX. It's also isomerization reaction here. So you have to have two reacts, separate step the reaction here. So between them, there is a flash drum or stripper here. What this does is, okay, you remove the latent stuff from the H2O reactor, just leaving the heavy normal paraffin feeding the second one. And the part of them is you recycle about 30% back to the front end. This recycle important is number one, can ensure your conversion of the reaction here. Number two, because the oxygen reaction is very active, you don't want this temperature run away. If it's too reactive, then the temperature will rising very fast, right? You blend a little bit from products to a feed to mitigate that. Going run up very fast there. Currently, there's dozens of the new technology available, but what we typically using is I will see those three ones most popular right now. We've been using top two right now, which is Honeywell UOP eco binding, heterotopsoil, hydroflex, X-Sync vacuum, right? All these quite similar three ones right now, which is available in the market right now, industry level. This is just a close take one of the project we designed here. It's a little bit detailed of the process here. Just to give you an idea how complex the units can be, right? So you can see that the feedstock, whatever the canola oil and fat, basically you have to feeding into the after heat exchanger here, feeding the first reactor here. The products goes to the flash drum here, and all the latent CO water get removed from top, and the bottom section, as I mentioned, partially got recycled back, and partially that is feeding to the second reactor here. And the second reactor affluents the final products. Basically, it's making isopropyl from normal paraffin. That final products, you get, there's a typical equipment here, we call it cold separator here. After you get cooling, we call cooling tree after cooling in a series exchanger and air cooler. Usually there's an important equipment we call the cold separator. In this cold separator, basically it's all the gas you recycle back, right? Which is still have like a 74, 75% of the hydrogen. So you make up a little bit hydrogen, recycle back to the reaction there. All the products actually is separated from the cold separator there. That products, you further send it to the low pressure process unit. Basically from the low pressure separation unit there, it's a series 3 or 4 different separation fractionation columns there. So you basically separated all those columns into different products, whatever you want, diesel or gasoline, right? It's all different products come from there. Okay. So the challenge is in this renewable diesel process here, reactors here. So okay, as you just mentioned, I specifically want to emphasize for the reactor design here. So number one, you have to design your catalyst very specifically for the specific purpose functions there. Basically, so you have catalyst has to be highly selective. So okay, so now the first one say hydrodeoxygenation is specially designed for the deoxygenation. The second one is a dewaxing specifically designed for the isomerization. Basically, it's changing the normal paraffin branches into other put side branches around the normal paraffin there. As mentioned there, this is you got a very high heat release from the reactors, the oxygenation reactor there. So basically, you have to dealing with those very high heat reaction. This is not easy duty for design and control. You have to put a lot more quench gas from my experience, basically your quench gas almost double or triple compared to the normal hydro treating reactors there. So that's for control those heat release is not a small target to meet there. The byproduct CO is also a headache for renewable diesel process here. That the CO, because this stuff you cannot remove from the amine. That's a process there. It stays there. Okay. There is no available technology specific design to remove this stuff there. So what people do here is just purge. Okay, you have to purge a big amount enough to maintain that CO level in the recycled gas back to the catalyst. Catalyst can withstand because it's a poisonous to the catalyst. It's deactivate the catalyst there. Right? That's a big challenge there. It's also increase your cost because the more you purge, the more hydrogen you have to add in there. So it's there's a separated reactor, and there is a high pressure stripper there for the different reaction steps are high pressure stripper. Some people use stripper, some people are just using a flash from there. Depends on. Okay. You are not only consider your reactor only, you have to consider the plant wise, right here. So when you design the plant, this unit in a new unit that usually fit in a refinery plant, you have to think about your plant wise there. From the feed line there, you are adding this stuff into your plant, which is not designed to handle it, especially for the cold property. You have to hold in the line temperature very hot to make the fluid confluable. You have to consider all those exchanger design. In one of the design, we have to shift one of the air cooler into the cooling water exchanger because the viscosity is too high. It's a pressure drop is too high. You are not able to get a good distributions as even distribution to each part of the air cooler there. So you have to change that function because of that. You have to put a sufficient margin in the off-gas handling, sour water handling of your plant because require more hydrogen. You have to check your hydrogen supply is it enough or not, right? Flare is usually design your flare, but when you're adding this unit to new unit to the plant, but you may not consider the emergency depressure from the high pressure loop. You have to consider that one when you design these units to the adding this unit to the plant, right? That's additional challenge for that as well. The last, not the least, is the corrosion issues here. Corrosion issues are specifically you have to emphasize here because that's a typical issue you have to dealing with when you consider this kind of design here. Okay, there are two sections you have to pay attention. The feedstock here, feeding line here. This is a low temperature region, but once you as soon as you put in renewable feed here, this one subject to the corrosions there. Typically, in conventional plant, this is common steel is good, but once you put a renewable feedstock, that common steel is not good anymore. You have to change into at least stainless steel. For the high temperature region, like from after heater here, you have to use maybe even high grade of the alloys or high grade of the stainless steel, like a 347 kind of material to handle those kind of stuff. Right? Those are cost pretty high. Yeah. Second region here is this one. These are corrosion issues. It's a typical phenomenon in any conventional hydrotreating unit there, but when you processing the renewable diesel, you add more issues to here because you have a higher content of the water coming from reactor, which was not there when you're dealing with the conventional feedstock there. So that one's making these corrosion issues even worse. This is what typical. These are usually this exchange along the line. Air cooler is give you a lot of headache in operation. Typically, they very subject to the corrosions here. Every refinery would have to change this kind of like exchanger once a couple of years there. Okay. For this renewable process, this equipment, you have to upgrade it very high grade of alloys. People talking about 825 or 625, which is very, very costly equipment here you have to use. A takeaway, okay. So challenges existed when you design a new hydrotreating unit in a renewable diesel process or co-processor biofeed with an existing hydrotreating unit there. The availability, quality, cost, or impact on the design should be considered when you're selecting the biofeed stock. You need to consider the corrosion issues associated with the biofeed stocks. You need to consider the coat properties associated with those biofeed stocks. And the consideration should also give into those very high exothermal heat released from those deoxygen reactor there. The process capacity plant-wise, I'm talking about plant-wise, dealing with the off-gas sour water treatment, you have to consider because you produce a lot more than you used to do it in a plant there when you design this renewable diesel process there. You have to consider your hydrogen balance. You consume more as well in the hydrotreating feed. So these are the major, very high level of the challenges that you are facing when you design your renewable diesel project. And that's all of my talking today. Thank you for attention. We're very happy to answer any questions. Thank you.